It seems like every time a new PC port comes out, we have a massive number of comments talking about this is unoptimized or the developers should have optimized this better. And we get this word optimized thrown out constantly by commenters, but how many of us actually understand what the process of optimizing a PC port of a game looks like? Like, what do they actually do? And as we look at this, this also goes into things I've been seeing recently when I talked about like CPU bottlenecks, for example. A lot of people talking about, are you bottlenecked by the CPU or are you bottlenecked by the game code? Especially when the game code isn't fully utilizing the CPU. How could you be CPU limited when you're not using 100% of the CPU? And I kind of showed games like that where we were CPU limited, but the CPU is like barely being used if you look at it as a usage percentage and all sorts of things. So the point is, I feel like actually hearing from a game developer who actually knows what they're doing when optimizing a PC port of a game, actually describe the process and track the performance uplifts and describe the difficulty of what they were doing is going to be very enlightening for both my audience as well as myself. Because while I might know more about this than the average random person, I am not a game developer, and especially not a game developer in charge of doing optimizations for a PC port. So while I've picked up some knowledge along the way, I think this is enlightening for me as well to hear from an actual game developer in charge of this process. Speaking of which, this is a developer talking about specifically optimizing Ease X on PC. I hope I'm pronouncing that correctly. This is not a series I actually play personally. But when I read this, it was super enlightening just about the optimization process, not so much about this specific game. And then also, I'm pretty sure the developer posting this, I recognize the name Durante as I'm pretty sure it's the same guy who did the mod for Dark Souls when it first came out on PC, that did a much better job of optimizing the game for PC than the actual game developers did. So that's pretty interesting. And here we can see in the versions how the performance improves, especially in CPU-limited performance situations, where they have graphics settings and everything turned up, but rendering resolution lower on a high-end system to reach CPU-limited performance. Anyway, we can talk more about those details in a minute, but what does the overall process of optimizing a game look like? So it looks like the first step is, again, before they even get to 0.1, is highlighting one of the challenges of optimizing games for PC performance compared to consoles, for example, which is the fact that with consoles, you have a very limited hardware and software set that you're targeting, right? Just which specific consoles are you targeting? Whereas on PC, you have all sorts of difficulties like AMD and NVIDIA graphics cards, and now there's even Intel Arc graphics cards, and they all have different drivers, and they respond to things differently and have different strengths and weaknesses. So one of the first things they noticed is that they had one of their main developer who actually has a high-end AMD system, noticing that performance would sometimes drop below 5 frames per second in certain circumstances. And they were able to identify this as a particular use of memory in DX11, leading to catastrophic performance loss on AMD, but they could solve the issue by changing the buffering implementation of GPU uploads. And they'd seen that before in a previous game they worked on, so luckily that wasn't a huge time sink figuring out what was going on here. But anyway, the idea generally being like one of the difficulties when optimizing a game for PC is having to account for all of those different hardware vendors and the differences in their drivers and how they interact with different APIs and all sorts of things, just being an added headache to what you need to test out and account for. And I can, this developer's not saying this, but I can personally account for, like, when I test out games when they first launch, sometimes I'll test them out on AMD, NVIDIA, and Intel Arc, and oftentimes you'll see one of them underperforming where it should. For example, when Starfield first launched, I couldn't even boot the game on Intel Arc, but it's possible that due to the low market share, did the developers spend much time testing it out and trying to get it to run on Intel Arc, GPUs to get ready for launch, right? So you'll sometimes see that being a factor in how well optimized a game is, which is having to account for all of those different types of hardware. And I'm not excusing developers for not doing that. We can see that these developers did identify an issue that was going on well before launch and solve the problem. But then, once the game's actually just up and running and interacting with the hardware in a reasonable sort of way, they reach version 0.1, where if we look at it in performance perspective, on this particular high-end set of hardware, it was achieving 106 frames per second. Maybe you're just like a game dev that's just like, okay, well, it's running at 106 FPS. The publishers want us to get this game out the door. Let's just publish it, right? We'll fix things later. And I think that's where a lot of people are feeling like PC ports are at. And honestly, I have no idea how often something like that actually takes place, or if it takes place at all. Because I think most game developers do want their game to run well, but do they have the time and resources and skill set to achieve that, right? So the point is, once the game's at least up and running, there is much low-hanging fruit that can massively increase performance without requiring a lot of work. And so we're hoping that at least most game devs go through that process. But what does that process look like, right? So that was kind of fun to get a little bit of an inside look here. And by the way, if you want to read this word for word yourself, I will link this source in my video description. This is just posted to the Steam page for this game as kind of a developer talk about the game. Anyway. So the idea here they're talking about for optimizing for CPU performance at the most basic level is that you look at a profiler output and try to optimize anything which seems to take an inordinate amount of time. That's where the low-hanging fruit idea comes from. At first, when you start optimizing, you can work on things that have a large overall impact and potentially achieve huge improvements very quickly. So what they're basically saying here with that profiler idea is a game developer has more access to, looking at how the game is performing, specifically what types of things the game is trying to do to output a frame, and which things are taking the longest, right? Because to output the next frame, lots of things have to take place for both the GPU and the CPU, and all of those things need to synchronize. And whatever's taking the longest is what you're going to have to wait for, right? You have a certain amount of time to get that next frame out, right? So if a certain thing is taking an inordinate amount of time, right? Something seems like it should be pretty simple, but it's taking a massive amount of the processing time for that frame, then identifying what that is and finding a way to do that faster is wiping out those low-hanging fruit. They said that the more optimized the software becomes, the harder it is to make further headway. Because once you've knocked out those really obvious, oh, that's a massive hang up on our processing time. Oh, there's another massive hang up on our processing time. You start knocking those out. Once you take out the big ones, it's going to be harder to make as impactful of steps. But they say that these ones are also the easiest ones to find. This is pretty visible in the overall comparison chart, especially if you consider that it was only a few days to go from point 1 to point 2, and then several weeks from point 2 to point 8. So what they're saying is like your initial oh, that's clearly a massive performance sink. Like, why is that taking so long? Knock it out, you'll get a massive performance jump in just a couple of days by knocking out the obvious issues. And again, once you've done that, it gets harder to optimize any further. So at what point does a game developer just run out of time and publish? You see what I'm saying? Anyway, but the point is, once they get this big performance jump, it then took a few days to do that, but now a few weeks to get this actually smaller performance jump from many smaller refinements, where you don't see quite as big of a massive time sink for one little part of the output flow. You get these smaller ones that are taking a little bit longer than other things. Can we tighten those up, right? And that takes a lot more time and effort. But still very much worthwhile. As you can see, they jump from 181 to 231 in those few weeks of optimization time. Now, this next part, the additional parallelization, I find the most fascinating, but also the most relevant to my discussions about CPU bottlenecks. And, for example, the people questioning, wait a second, how is it a CPU bottleneck if the CPU is only like 50% utilized, right? I get a lot of comments like that when I mention a game is CPU bottlenecked, where you're like, the CPU is barely being used. What do you mean by a CPU bottleneck? And a lot of people then talk about this being this isn't a CPU problem, it's an engine problem or an optimization problem. And my take on that is those things are all related, right? The CPU is running code. And if that code is executed more efficiently, it can mean the CPU can output more frames in the same amount of time. But what we mean by CPU limited performance is that in essence, the game is waiting on tasks that the CPU is trying to calculate, right? Now, as we can see here, all of these frame rates are the exact same scene in the exact same game in CPU limited performance. But as the game code is rewritten in more efficient ways, the game code is optimized, the game is able to perform a lot faster on that same CPU while still being CPU limited. At every single point, this was CPU limited, but the game code can be better optimized to run on that CPU. However, that doesn't necessarily mean, notice that these big jumps here, we're not, going from 106 to 181 to 231, none of that was actually increasing the parallelization of the game to use more CPU cores, which is related to the question people often have of, wait, how can you be CPU limited if your CPU is only sitting at like 50% utilization? And that has to do with parallel tasks, the number of threads the game is trying to calculate at the same time, and whether that's beneficial. Because as I described in my GPU bottleneck video, my understanding is that a lot of the things the CPU is doing in a game are very, very, very difficult to split up into parallel threads and then tie back together in a manner that actually improves performance. So let's hear, but that's me. I'm not a game developer. So let's hear from an actual game developer in charge of this type of optimization, what they have to say about that topic, about the challenge of adding in additional parallelization, how you can get more performance from it, but how it can be very difficult to achieve and even questionable whether it's a good idea in some circumstances. So, let's actually read this one a little more word for word, because I think this is kind of the meat of, I think, what's most interesting in this video. So this is by far the most exciting step, and also the one that is really a rather questionable idea. Look at that. The idea of trying to get more parallelization here is being described as a rather questionable idea. Why? Why questionable? So let's look. When we started to work on the port, the game had a main update thread, a graphics thread, and several background threads for audio and asynchronous tasks. Of those, only the graphics and main update thread do any real CPU work, and only the main thread was limiting performance. So again, this is describing these situations where how do we have the CPU showing nowhere near 100% workload, but I'm still claiming this is CPU limited performance, right? Well, that's what the game developer is describing here, is that what's happening is the CPU work is split into a certain number of threads, but oftentimes there is a main game thread that everything else needs to sync up to in order, and like that's the one with most of the work, and the game cannot run any faster than that main thread. So that was limiting the performance, right? But can you do anything about that by splitting up that work into more threads? And that can be challenging, right? That's why he's describing this as maybe even a questionable idea. So looking into that main update thread further, we discovered that a large chunk of time is spent updating all the actors in the scene individually. That includes characters, monsters, pickups, and basically everything else you can see, as well as some things you can't see, such as event triggers. So the basic idea is rather obvious. Perform these updates in parallel. And again, this is what I was talking about in my GPU bottleneck paradox type video, where I'm talking about how in scenes that I'm choosing to show CPU bottlenecks, I'm often choosing to be in a town. Like in this case, we're looking at the town of Hogsmeade, which is often way more CPU bottlenecked than if I was just running out in the wilderness in the same game. Because this is where there's tons of NPCs and objects and everything all in the same area, and the CPU is having to handle all of that logic. So obviously we're not looking at a game developer talking about this specific game, but I'm giving an example of that's the type of thing that tends to be difficult for CPUs to handle and often creates CPU-limited performance in a certain scene of a game rather than in all scenes of the game, if that kind of makes sense. Anyway, so the idea is, can you split that work up into parallel? So the game developer continues, of course, in reality, it's not quite that simple. Since each of these update steps can and will interact arbitrarily with some global system or state that was developed under the assumption that everything is sequential. The surprising thing is really that we got it to work, but a lot of development time went into debugging problems that arose due to this parallelization. Ultimately, due to the level of synchronization required, the actor updates only really scale up to 3 threads. But the improvement is still substantial, especially since it is most pronounced in the hardest to run areas. Those are the ones with more individual actors. So again, notice this. This is a game developer that is doing something that is very difficult and putting in a lot of development time to make this happen and overcoming a lot of challenges related to the fact that all of these things need to synchronize, right? So it's hard to parallelize stuff onto separate threads that might need to interact with each other in some sequential way, right? So that's a very difficult challenge. And they said they were still really only able to scale that up to 3 threads. So that's where I'm saying that, okay, a lot of times you are CPU limited when you're not using the full CPU cores. Because let's say you're on an 8-core CPU, but the game is really only running challenging work on 4 threads. Well, then you'll be at maybe those 4 threads are maxed out, but you're only showing 50% CPU utilization. And then you can claim that that's just bad optimization from game devs. And that's what I see a lot in the comment section, where I just want us to make sure that we're a little bit careful about that, because there are absolutely games that are poorly optimized, but a game not using a massive number of cores and threads is not in and of itself an indication that developers didn't put a lot of time into trying to use as many cores and threads as possible. And as this game dev is explaining, they put a lot of development time into this and were able to get a lot of performance improvement. But in the end, they were still only able to scale that work up to 3 threads. So if you're on a 16-core, 32-thread CPU, you're still going to have a lot of cores and threads not being used and show low CPU utilization, even if you are actually CPU limited and the game code has had a lot of work put into parallelizing it and trying to optimize it. But they are saying that the improvement was still substantial for putting in that work. And so it's nice to see, game devs actually putting in that large amount of work to make that happen, which is pretty cool. If we go back to the performance graph, we can say that was going from 231 to 293. Notice that massive amount of work and time was less overall performance gain than what they got from, low-hanging fruit and small refinements, where if you combine all that together, they more than doubled performance. But going from here to here was definitely not doubling performance, right? So you can see where at some point, a lot of game developers probably just, publishers like, we need to get this game out the door, it's costing us money, they might ship before that was all of that extra work into the parallelization is maybe as complete or, efficient as possible, right? But it's cool to see this game developer talking about that process. Anyway, so then they do have one last step they describe here, which is GPU query and input optimizations. And you can see they didn't get a lot out of this, 293 to 314. So just a little bit of extra, but that's not the full story. The overall frame rate isn't the full picture. And that's another thing they talk about here. Because in addition to how fast does a game run, there's also the question of how smoothly does the game run? What does the frame pacing look like? And that can be represented visually by a frame time graph. And that's what this next section is talking about. So this next part, talking about GPU query and input optimization, they're saying in version 0.2, look at this frame time graph. It's honestly not the worst I've ever seen. I've seen things a lot worse than this, but it is, wavering up and down a little bit. Whereas if you look at the release version, it looks extremely flat. It looks so flat that the developers actually explain that that flatness is shown without a frame rate limiter or VSync, because usually you only see that flat of a frame time chart when one of those things is engaged, when you're actually using VSync or a frame rate limiter to cap the frame rate and get that nice frame pacing, which is one reason why a lot of people frame rate cap when they're playing games, is to increase the smoothness of playing, even if you could at times reach a higher frame rate. Sometimes it's a better experience to actually cap your frame rate at a point where the game can run smoothly and consistently. But anyway, that's kind of its own topic. So how did they go from the wavery frame time graph to the smoother frame time graph? They said the final step on that optimization journey was more related to improving frame time stability at high frame rates rather than just pure performance. The image above shows a frame time chart comparison. I kind of already explained that. So then they said, well, what did they do, right? What they did here was purposefully introduce a 1 frame off synchronization point between GPU and CPU progress. The developers saying that their initial thought was that this would improve stability, but reduce frame rate. And so it would have to be a setting that maybe users could choose if they wanted to use it, because it might have a performance cost, even though it helped stability. But he said when he actually did it, it had the unexpected effect that it actually improves both performance and the frame rate stability, the frame time smoothness. And he says he's not 100% sure why, but his theory is that it has to do with thread scheduling decisions from the OS being improved in that case. So again, part of the thought is like, even a game dev who clearly knows a lot about optimization is making some choices. Sometimes get surprised at what happens. And then they also mention a little bit about improving performance in the presence of high polling rate mice. And they have a separate article getting into the weeds on that. So hey, you could follow up on that, but I think it's beyond the scope of what we're talking about in today's video as well. And then he also says something that they lied to us in the initial thing, because if you look at this original graph where it says that this is CPU limited performance with maximized draw distance and set location with identical quality across all versions, what they actually mention is, believe it or not, it's not identical quality across all versions. The more performant version is actually running with better quality, in the sense that the animation smoothness was actually updated more frequently in the more optimized code. So it's actually going to look better than the original build, and they were still able to do that while increasing performance. So you can see overall this optimization process has basically tripled the frame rate originally. And compared to the low-hanging fruit, has still, I mean, not quite doubled it, but made a massive performance difference compared to the low-hanging fruit. However, that being said, the game is still not, going to use all 16 cores and threads on some big CPU, meaning this is probably not a game where you see full CPU utilization. But again, does that mean the game is unoptimized, right? Probably not. Anyway, so it's really cool to hear a game developer, talk in detail about what this overall process looks like, what it entails from the developer perspective. And again, I especially liked hearing about the challenges of the parallelization, because again, it kind of backs up the fact that in and of itself, not being able to use some arbitrary number of cores doesn't necessarily mean development time wasn't put into optimizing that. You can just sometimes only split that off so far if they have to sync back together at certain points. But that it can absolutely be worth putting in some development effort into getting that as much as possible. So anyway, hopefully you guys found this enlightening about what do we mean when we actually talk about optimization and what an optimized PC game looks like. Because optimization isn't just about the game performing well or badly. It's just about how well can you get it to perform, executing effectively the same thing, right? So this is all basically running the same thing, but by changing the code, your CPU limited performance. You were CPU bottlenecked in all of these cases, but the performance numbers have changed drastically based on the code being rewritten to be more optimal. So anyway, cool stuff. Hope you guys found it useful and or interesting, and I hope all of you have an excellent day.